Assalamu alaikum. It's our problem solving lecture of principal methods and applications of nuclear tracks. In this lecture, we will only solve some problems related to this concern. Okay, so let's start with the first problem we have here. An alpha particle has an energy of zero point 0.5 mega electron volts. Okay, and a constant value A equals to 1.2, whereas B equals to zero point 0.5. Okay, so the value of constants is given. You have an alpha particle energy is also given, that is zero point 0.5 mega electron volts. You have to find the range. So how you can find the range? There is a formula, as you know, that by Nutter-Gigel law, the empirical formula which we can use for the most energetic alpha particles. So whereas this problem is concerned with the alpha particles, so that we have to use this formula, which is minus ln of t, whereas t is the kinetic energy of the alpha particle, equals to a plus b, whereas a and b are the constant expressions. Ln of r is the range of the alpha particle, which we have to find in this problem. Okay, so what you have to do to finding the value of r, just add a and b and move to the other side, divide by minus ln of t. This is minus ln of t. T value is given, which is 0.5, divided by a plus b. A is 1 plus 2, b is 0.5. After adding, you will get 1.7. So u equals to ln of r as it is. So after taking this, you can see in the calculator, after solving this you will get 0.4. So here is 0.4. Okay, 0.407 equals to ln of r. So that we need the value of r, so we have to remove this natural log. So how we can remove this natural log? We have to take the exponential here and exponential here. It comes in on the power of the exponential, and after taking the exponential power, you can see that you get your answer, and your answer is 1.503. So this is how you can find the range of an alpha particle, means more energetic alpha particle, if the value of constants are given. So now let's move on towards our next problems. These problems we are going to solve, these problems are related to alpha decay, your beta emission, and the numericals concerned with alpha, beta, and gamma decays. So let's start these problems. Here is our another problem of chapter number 3, book James E. Turner. Okay, and problem number 12, what it says: calculate the energy released by the alpha particle decay of radon 222286. You have to first of all calculate the energy released, means you have to calculate the q value. Secondly, b, calculate the energy of the alpha particles. Now you have to calculate e alpha in the b part. And what is the energy released of the recoil polonium atom, means you also have to calculate the residual energy, because you see here that your radon is converted into the polonium plus alpha decay, means helium atom. So first of all, you calculate the q value, then you have to calculate the e alpha, means energy of the alpha particle, and lastly you have to calculate the energy of the residual particle. In this case, this is polonium. So let's start by finding the q value. This is alpha decay, so you know that in case of alpha decay, you have to, how you can find the q value? By parent minus daughter. Parent is radon, which is the mass number of radon is 222.0175. This must be given in your problem, minus daughter here are two, polonium plus helium, because minus polonium and minus helium, it becomes minus mass of polonium minus mass of helium. To convert this in mega electron volts, you have to convert AMU into mega electron volts. You know that one atomic mass units is basically equals to 931.502 mega electron volts. So after calculating, you will get your answer of q value of this alpha particle decay, and that is equals to 6.520 mega electron volts. Now you have to find the energy of the alpha particle. You know that how you can find the energy of the alpha particle. Basically, it's equals to q m, capital M, which is the mass of the residual, divided by small m plus m. capital M. Small m is the mass of the basically alpha particle, and capital M is the mass of the residual particle. Small mass is helium mass, alpha particle is helium, so 4 plus residual mass, because polonium has mass 218, so 218. Q value we already find it 6.520 here, and mass is the mass of polonium. After calculating, you will get your answer, and your answer is 6.40 mega electron volts. Now you have to calculate the recoil energy, means residual energy, and in our case residual energy is the polonium atom. For polonium atom, as we know that your total energy, your total Q value is always the sum of alpha energy plus the recoil energy. Q value we already find it here, E alpha we already find it here. We have to calculate E recoil, so E recoil becomes equals to Q minus E alpha. Q values is here, E alpha values here. After subtracting, you will get your energy of the recoil, and that is equals to 0.1 mega electron volts. So that's all for this problem. Now our next problem is problem number 13. The uranium 23892 nucleus emits a 4.20 mega electron volts alpha particle. Now the alpha emitted particle energy is given, and that is equals to, yani means E alpha equals to 4.20 mega electron volts. Okay, E alpha. And you know that the small m is basically the mass of the helium atom, basically alpha particle, and this capital M is basically the mass of the residual particle. In this uranium 235, you know the expression, uranium 238 basically decays into thorium 234 90 plus an emission of alpha particle, definitely amount of energy release. So this capital M is basically the mass of the thorium, and mass of thorium always given, and that is equals to 434. Understood? Because the E alpha value is given, what you have to find, what is the total energy released, means you have to find the Q value. By knowing the value of E alpha, you can easily calculate the value of Q by knowing their masses. So E alpha value is given 4.20. Masses are always given for alpha particle and for recoil particle, and recoil particle in our case is thorium 234. After calculating, you will get your answer, and your answer is 4.27 mega electron volts. So this is basically the total energy released in this decay. Understood? Now move on towards our next problem number 14. What it says, the radon 22688 nucleus emits 4.60 mega electron volt alpha particles. Now again the energy of alpha emission is given, and that is equals to 4.60, means E alpha is this 5.5% of the time when it decays to radon 22286. Radium decays into radon, definitely it emits some alpha particle, and alpha particle is the helium atom. Okay, calculate Q value. Again you have to calculate the Q value, then you have to calculate the energy of the recoil, means the residual energy of radon, because your radium is converted into radon, so you have to calculate the energy of radon. So first of all, let's start by finding the value of Q. How you can find the value of Q? You know that the expression of Q is basically equals to E alpha multiply M plus M divided by M, whereas your small m is the mass of the alpha particle and capital M is the mass of residual particle. So after putting the values, 4.06 is already given for the E alpha value, and small m is the mass of helium atom plus mass of the residual atom. In our concern is the radons. After dividing by mass of radon, you will get the Q value. Because our concern is to find the recoil energy, you know that the total energy is always equal to sum of recoil and sum of alpha. And if you want to find recoil, so it becomes Q minus E alpha. Q is this we find here, and E alpha is already given here. After subtracting, you will get your energy of the radon, means recoil energy is equals to 0.08 mega electron volts. Okay, so now let's move on towards our next problems. This is our next problem. What it says, this problem is related to carbon dating. A piece of charcoal contains 25 grams of carbon, is found in some ancient city. The sample shows a carbon C14 activity which is equals to 250 decays per minute. How long has the tree formed his charcoal came being death? Okay, so you have to find the time, how long has the tree found from this charcoal came being dead. So you have to find the duration, means time. If the a piece of charcoal mass is given, which is 25 grams of carbon, okay, and the activity of also given, which is 250 decays per minute. So you have to find time. How you can find the decay time? You can find by this relation, t equals to minus 1 by lambda, whereas your lambda is basically the decay constant, ln of r by r naught. Understood? This is how you can find the time period. So let's start our this problem. So you know that in our time period relation there is a factor of r by r naught, and r by r naught basically equals to r divided by this r naught changes into lambda n naught for C14, because in our problem C14 is involved. Okay, again this further changes into r divided by lambda r naught n naught. Understood? We also know that lambda is, which is the decay constant, is always equals to ln of 2 divided by t1 by 2. Okay, t1 by 2 is basically the half life of the material. So here is the lambda. It further reduces to this n naught changes into small n, and na is the Avogadro's number. Now you have to put the value of lambda, which is this ln of 2 divided by t1 by 2. So r by r naught becomes r divided by r naught ln of 2 divided by t1 by 2, and this small n number of moles basically changes into mass in gram divided by molar mass into Avogadro's numbers. This capital M goes upside, so your, and this t1 by 2 also goes upside, so your final relation of r divided by r naught becomes equals to r m t1 by 2, okay, divided by r naught ln of 2 m multiplied by Avogadro's number. In our case, the activity is given, the activity of C14R is given, which is 250 per meter, okay, decay per minute, okay, whereas T is the half-life, and we know that carbon 14 has a half-life of 5730 years, okay, where mass is also given, okay, 12. Because we are concerned with the carbon atom, carbon has a mass number of 12. R naught is basically the constant, and its value is always 1.3 into 10 raised power minus 12 meters. And ln of 2 multiplied by small m is the mass number is given in grams, which is 250, and molar mass I already told you is 12 grams per mole, and multiplied by Avogadro's number. Okay, so by calculating you will get your answer, but your answer is in year per second, so you have to convert year per minute, so you have to convert year per minute. And you know that 1 year has 3.15 into 10 raised to 7 seconds, and 1 minute has 60 seconds. So after multiplying your answer of this, multiply by this, divide by 60, you will get your final answer, and your final answer is basically 3.4 into so your final answer is then equals to 0.667. Now this is your answer of r divided by r naught, but you have to find the time, means decay time. So you know that the formula of the decay time is basically equals to 1 by lambda ln of r by r naught. So r by r naught is this, which is 0.667, and minus 1 by lambda, lambda value, you know that ln of 2 divided by t1 by 2, ln of 2 t1 by 2 comes upside. So putting the values, you will get your final answer, and your time of decay is basically equals to 3.4 into 10 raised per 3 years. Now move on towards next problem. Similar problem, what it says: consider an ancient mummy having a mass, again molar, again mass given in grams, which is 125 grams, found in Egypt. The sample shows activity of carbon 14 is again given, which is 350 per decays per minute. Find the age of the mummy. Again you have to find the age of the mummy, means how long time being goes for this mummy. So again the mass in grams is given, and the carbon 14 activity is given, which is 350 decays per minute. We have to find age, means you have to find time. For that you must have to first of all know about the ratio of r by r naught, and you know that the ratio of r by r naught is equals to r capital M t 1 by 2 divided by r naught ln of t n a and small m. Okay, where small m is the mass in grams and capital M is the molar mass, because again we are concerned with the carbon 14. So the molar mass of the carbon 14 is basically equals to 12. So after putting the value of this R activity, which is 350, multiply the molar mass, which is 12 grams per mole, T 1 by 2, half life we already know for the carbon atom, half life is 5730 years. Okay, again putting the value of r naught, which is constant as I mentioned before, this is 1.3 into 10 raised to minus 12 multiplies by ln of 2 multiplies by the mass in grams, which is given in this case is 125 grams, multiplies by Avogadro's number, you know that 6.02 into 10 raised to power 23 per mole, but your units come into years per minute, and you know that 1 year has 3.15 into 10 to 7 seconds divided by 60 seconds in 1 minute, because the ratio of r by r naught has no unit. So if, because this is a ratio of same aspects rr, so it has no unit, so to conserve units you must have to multiply the answer of this, multiply by this, divided by 60, you will get your answer, and your answer is 0.1866. Because you have to find the age of the mummy, means the time period, you know that the formula of the t is basically equals to minus 1 by lambda ln of r by r naught. By putting the value of lambda, you know that lambda is basically equals to ln of 2 divided by t1 by 2, ln of 2 here and t1 by 2 comes upside, minus is with him, and ln of r by r naught, and the value of r by r naught is 0.1866. Half-life of the carbon 14 is, as I mentioned before, 5730 divided by ln of 2 multiplies by ln of 0.1866, and you will get the time period for the case of mummy in this problem is basically equals to 1.3 into 10 raised per 4 years. So this is the age of that mummy. Now move on towards our next problem, and our next problem is basically the topic from fission tracks dating. Let's start. The problem is, consider we have to measure the age of the rock uranium-238 using spontaneous track density technique. The information provided as the density constant is given. Lambda is equals to 8.46 into 10 raised to minus 17 per year. Okay, whereas the time of the spontaneous fission is also mentioned, 1.5 into 10 raised to minus 6 per year, and the number of atoms per unit volume also here, which is 2.5 into 10 raised to 22 atoms per centimeter cube. If the fraction of uranium-238 in natural uranium is 0.9927 and the length of the etchable track is 10 micrometers, and the efficiency is also here given, and that is 0.85, what you have to find, you have to find the spontaneous track density. So there is a formula of the spontaneous track density. Here I wrote, here is the formula for the spontaneous track density. Rho s equals to a lambda, whereas a is basically the time our spontaneous fission. Lambda you already know very well, it's basically the decay rate. In our problem is uranium-238, so yes, this is the decay constant of uranium-238 in this problem. And n naught C238, n naught is basically the number of atoms per unit volume in material, whereas C238 is basically the fission of uranium-238 atom, multiplies by R238, R, which is the length of the etchable track, eta 238, eta is basically the etching efficiency. By multiplying all these aspects, then you will find the spontaneous track density. Understood? So all these factors are given in our problem. Like this is the value of time our spontaneous fission, and the value is given, which is 1.5. You can see time of the spontaneous fission is 1.5 into 10 to the minus 6, the value of a. Then the value of lambda, means decay constant, is also given, 8.46 into 10 to the minus 17 per year. Then the value of n naught, which is the number of atoms per unit, this you can see number of atoms per unit volume is also given 2.5 into 10 to the 22 and multiplies by C238 fraction of uranium 238. The fraction of uranium 230 is also given. You can see the fraction of uranium 238 is given 0.9927. 0.9927 multiplies by R238. R238, which is the length of the etchable track. The length of the etchable track also mentioned 10 micrometers, mean 10 multiplied 10 raised to power minus 6. And lastly, the efficiency is also given here 0.85. After multiplying, you will get your answer 2.5 into 10 raised to power minus 5 atom meter per year square centimeter cube. So to convert your units into atoms per centimeter square, so your track spontaneous track density is 2.5 into 10 raised to power 10 per centimeter square. Another problem similar with from this topic, and the problem is now the number of uranium 238 atom is 3 multiplied 10 raised to power 22 atoms per centimeter cube, whereas the fractional atom of your C238 is given 0.9927. If the length of the etchable track uranium 238 fission fragments is 8 micrometers and the efficiency is 0.9, while the decay constant of uranium 238 is 8.46 into 10 raised to power minus 17 per year, and the time for the spontaneous fission track stored is 2 multiplies by 10 raised to power minus 6 per year. What you have to do, you have to find the track density of uranium 238. So to find track density, again you have to multiply a by lambda. This is the value of a, which is given 2 multiplies by 10 raised to power minus 6 here, which is the spontaneous track, and the value of decay constant 8.4 into 10 raised to power minus here is given minus 17 multiplies by this 3 multiplies by 20 10 for 22, which is the number of uranium atom, and multiplies by 0.9927, which is the fraction of atom of C238, multiplies by R238, and R238 is given, which is 8 multiplied by 10 raised to power minus 6. And lastly, the other thing is you can see micrometers, 8 multiplied times by minus 6, and lastly the efficiency, which is 0.9. After multiplying, you will get your answer of the spontaneous track density is equals to 3.62 into 10 raised to power minus 5 atoms per centimeter square. Understood? Okay. But what if you have to find the induced track density? Here is another formula for induced track density, which is this sigma psi n naught c 238 r 235, sorry, eta 235 r 235 c 235 n naught and sigma phi, where sigma is basically the cross section of uranium 235 and psi is basically the thermal neutron per unit area. Basically your induced track density whenever you are concerned with the 235 atoms, you can see here, and whenever you are dealing with your 238 atoms, you are finding the spontaneous okay track density. If you want to find age, so here how you can find age is equals to summation multiplies by rho s spontaneous track density divided by induced track density multiplied by another rho d, okay, whereas rho d is basically equals to b psi. Understood? Okay, whereas this summation is equals to sigma divided by b lambda c235 r235 eta 235 divided by c238 r238 and eta 238. So this is our numerical problem sessions of principal matters and applications of nuclear tracks. We do some 5 to 6 problems in this lecture, and that's all for this lecture. We will upload more interesting lectures of this course and problems and assignments, quizzes. So stay tuned with us. If you have any query, you can comment in the description below. I can definitely answer your precious questions. Till then, if you forgot to watch previous lectures, we have till now 10 lectures of principal matters and applications of nuclear tracks. You can go through all those lectures. Till then, take care. Allah Hafiz.